conversations, but we are about to get ready with our next session. So our next speaker is Dr. Sunny Narayanan, and he is currently a research faculty at Florida State. Sunny holds a PhD from Texas A&M University in medical and space physiology, and a BS degree from West Virginia University in mechanical engineering and biology. Sunny took his first professional steps with NASA supporting systems engineering computational projects at the Katherine Johnson Independent Verification and Validation Facility, completing team-based design build fly projects through NASA's Microgravity University program, and conducting nanotechnology biomedical research as a Ronald E. McNair Scholar. He continued his academic steps at Texas A&M University, supported by the National Space Biomedical Research Institute, for his doctorate to study physiological adaptations of astronauts during their journey in space. His doctoral work also involved opportunities at Brookhaven National Labs, International Space Station spaceflight biomedical projects, National Institutes of Health funded studies, and NASA Kennedy and Johnson Space Centers. Now, as a research faculty, he continues his support of NASA's space program, leading and supporting multiple biomedical studies investigating the physiological effects of deep space radiation, lunar and Martian gravity, relevant to our human space exploration goals as we return to the moon and beyond through the Artemis program. And now I am very happy to introduce Dr. Narayanan.
Thank you, Cassie, and thank you all for joining us today. And wow, the years have flown by. But in short, Cassie has shared a few of the wonderful and incredible experiences I've had the opportunity to be a part of through academics. And today I aim to present my perspective, my experience with as a researcher, as a scientist, how coincidentally open science projects inspired me initially to learn about science, and in turn now have the opportunity to be involved with some similar open science projects as a researcher here at Florida State University. Integrating my experiences, background, perspectives, as well as connecting with students and broader community with regards to our different areas of interest. So I begin with sharing a little bit about the TOPS program, a program involved with NASA, Transform Open Science Initiative, which is related to NASA's many different program directives. So I'm primarily a researcher with support with NASA. I'll provide an overview of some of the NASA programs I'm familiar with, and then specifically the projects I'm involved with NASA. So in short, NASA is a U.S. federal agency that has a number of different program areas focusing on a number of different subjects, from aeronautics to exploration systems to science to space operations to space and technology, with NASA Aeronautic and Space Administration having specific project areas. And in turn, each of these project areas have additional areas of focus, and here in short and brief provide some background and further examples of these different directorates. Aeronautics, for example, includes NASA's efforts in air transportation, aviation industry. If you ever were, for those that have been on a plane before, NASA had likely a involvement in the design, development, manufacturing of aircraft and more recently or historically. NASA also has areas involving exploration systems, which include the Artemis program that Cassie just shared a few moments ago, which include the design, development, and building of the different components of that. Current example includes the International Space Station, which is a orbiting spacecraft, a satellite that travels around the Earth every 90 minutes. Has had people living on board the International Space Station for decades now. Took many years to design, build, and launch, and be assembled in space. And the Artemis program is, and there have been projects even before the ISS that led to the support and development of ISS. But building on the history, the experiences from that is Artemis, which I'll elaborate more detail later, but it's a continuation of our space exploration adventure to the moon and around the moon and beyond. And related with that include space operations. Space operations, as the term suggests, includes any type of activity in space, primarily low Earth orbit, which just refers to the area immediately outside Earth. And the International Space Station is an example of a spacecraft that is involved with space operations. And the International Space Station, in turn, is not just a habitat for that's orbiting our planet, a satellite, and has people on board, but is also a environment that enables us to do some incredible science and incredible space technology development, with space being a very different environment from here on planet Earth, having different environmental factors. Two examples include there's a different gravitational field on the International Space Station. Individuals and materials and items on board the International Space Station, because of its the way it's traveling, experience a lack of gravity. So, for example, astronauts, when they're on board the space station, they are floating. And in turn, with them specifically, cause them to develop various adaptations to that very different environment. And in turn, there's been, so the International Space Station actually is a national lab, in the same way that Florida State University's MAG lab is a national lab. So it is, IS is designated also as a resource to conduct science and technology development. So I'll share a little bit more with my specific experience in the context of science, but NASA's science mission directed includes topics such as Earth science, planetary science, so studying Venus, Mars, additional planets in our solar system, as well as exoplanets beyond our solar system. Biological and physical science, the area of research I'm specifically involved with, space biology, studying how when biology travel into space and are exposed to the unique environment of space, how those organisms and biology potentially adapt. And then there's also heliophysics and astrophysics. Astrophysics focusing on like the Hubble Space Telescope, studying the distant stars and galaxies in our universe, and galactic cosmic background radiation. And heliophysics, so studying how the behavior of our sun, for example, and its solar cycle, and how and space weather, how solar flares may influence and affect us here on Earth. And then space technology, with the International Space Station being an example, again, requiring the development and design of hardware materials, structures that can sustain being in a space environment. The International Space Station is an environment where temperatures go from negative a couple hundred degrees below 0 Celsius to a couple hundred degrees above 0 Celsius every 90 minutes. So there are huge temperature fluctuation gradients, and it's a vacuum. There's no atmosphere. There's radiation. There's constant exposure to particulates, micrometeorites, traveling at very, very high speeds that collide with the space station. And in turn, it's remote, so it's in space. It's not, unfortunately, outside our building here. And if there's a maintenance required for that, I couldn't very easily walk outside the building and take care of whatever maintenance issue there may be. And it's been in space for almost 20 years now. So it's been an incredible platform for a number of different technology development opportunities as well, that in turn have led to a number of spin-offs to Earth. So there's NASA about a year ago, I believe, released a library of patents that a few universities now have access to, Florida State being one, in terms of all the technologies and inventions that were created through through technology innovation and science with NASA's program. So TOPS is a initiative through NASA that aims to provide a platform for open science practices. And as Cassie shared earlier, NASA declared 2023 as the year of open science, and NASA has highlighted as a 5-year journey, so to speak, but likely beyond that as well, with the intent of accelerating major scientific discoveries. As well as broad participation of NASA programs and opportunities and resources to historically excluded communities, as well as another mechanism to increase our understanding and adoption of open science principles and techniques in the context of NASA's projects and opportunities. With the objective to broaden participation, increase accessibility to knowledge, and in turn embrace new technology that can respond to these changes at scale. Some of the examples I had shared in brief with the example I gave with regards to NASA's different directorate programs. But through the mechanism of NASA's Open Science program, which I'll share a little bit about in more detail from my experience as well. And in turn, NASA's TOPS program has released resources in similar subject matter that have been shared by the previous speakers and additional organizations as well. One example being a data management plan in the context of NASA's requirements to archiving data, software publications, and eligibility to funding in the context of NASA's specific projects. So how am I involved with these open science initiatives? So having share a little bit about NASA and the TOPS program, and thank you, Cassie, for the introduction. I thought I'd share a little bit about my academic background and training and experience that have guided my perspective towards research and open science. And I would like to share it in this context that I'm also a first-generation academic. I'm the first in my family to go to college. I was also a Pell Grant Title I student. It was academics that really opened up a whole new world in many ways for me. To see and experience subjects and projects that I only imagined at one point. And in turn, I'm also first in my family to be a scientist, first in my family to be an engineer. So for me, it was academics is a wonderful way to learn what science was or what an engineer was, having an aptitude for these subjects, but not necessarily having the guidance to know what a scientist was, or what an engineer, et cetera, was. So that's where my early academic exposure with the specific training experience I had really provided me with guidance, and led to my specialties in interdisciplinary research and engineering, and being involved with projects that we've had the wonderful opportunity to travel through the International Space Station, and also ground-based analog systems where we simulate different conditions of spaceflight, simulate a lack of gravity, radiation exposure through experiments at our lab at various NASA facilities like Brookhaven National Laboratory, studying fundamentally how our biology adapts to that space, to these environments, but also providing a new perspective to approaching medical research as well, in the context of how gravity, an environmental factor that I'm setting up, if I were to sit down, would have an instantaneous effect on my biological processes. But we can't really study that here on Earth. The only place we can truly study that is in space. And I'll elaborate a little bit more on that detail of the specifics of that later. And in turn, also increasing our access. So from my own experience, recognizing the wonderful opportunity that academic projects have but broadening that to through open science mechanisms to a broader community of students and young professionals that I'll share more detail of a ongoing open science project that we have. So for me, I'll start a little bit about my how specific experiences guided my intern open science projects, where I recall in middle school an opportunity. So Cassie mentioned a NASA center, the Katherine Johnson Independent Verification Validation Facility. I grew up in Morgantown, West Virginia. The IBMV facility was driving 30 minutes away from Morgantown, West Virginia. And I recall a middle school event where NASA civil servants visited our middle school program and shared that this center existed, and shared what prelude what NASA engineers did, and what kind of projects were at NASA IBMV, and learning about the opportunity to get involved as a high school intern at this NASA center, and had the wonderful support and opportunity to, and later in high school, to be an intern at this facility, be involved with computational programming models, simulating primarily spacecraft rockets, the space launch system that launched, Artemis 1 rocket that launched just last year was when I was a NASA intern, called the Ares 5 rocket. So I was on with a different project, Ares 1 rocket, but that was my first project introduction of engineering subject matter, but hands-on experience and at the high school level in terms of being introduced to computer science and engineering subject matter. At the high school level. And then continuing my education at West Virginia University, being involved with coursework in my mechanical engineering and biology courses, but also being actively involved with research projects. For me, supported by NASA, including the design and development of a project that fluid mechanics focus, with the theme being focusing how similar different states of gravity have an effect on how fluids behave, and thinking about ways to design systems to control how fluids behave. And we used our idea. We're using nanoparticles, and I'll share why nanoparticles in a moment. But so we had the we as undergraduates had the opportunity to the picture on the top right is of us in front of the aircraft. Behind us is a DC-9 aircraft that NASA uses to simulate differences of gravity. It goes in a parabolic flight, goes up and down, and everyone on board, experiments included, experience short durations of micro, lunar, and Martian gravity, depending on the time of the flight. And we also experienced those, so that was a very unique experience in many ways. But to see and be involved with these research projects and apply our experience in the course led to additional inspiration in the context of, well, here I am floating for 20 seconds. This is certainly a very unique experience. Now, astronauts are also, this is happening to astronauts as well. And they're traveling in space, but they're in space for longer periods of time. So we were curious, well, what happens with astronauts? Do they experience the similar adaptations that we experience in a very short period of time? And that experience, that exposure inspired me to think about the question of what happens to biology, what happens to people when they travel in space. Which connected with my research interests in biology and medicine. So I was, Cassie mentioned, I was a McNair Scholar, Ronald McNair Scholar program supporting first-generation academics, individuals from underrepresented backgrounds in academics. And the research opportunity through this program enabled my experience in nanotechnology, nanoparticle research. And it was that biomedical research experience and that exposure to nanoparticles which was what led to the interdisciplinary project with regards to our microgravity research projects, and enable that connection to be made across very different disciplines, and to tackle very relevant problem that NASA had in the context of with space operations, with missions to the moon and beyond, by the interdisciplinary projects that we as a team approached together. And in short, have continued these efforts as a graduate trainee at Texas A&M, now formerly as a postdoctoral fellow, and now as a research faculty here at Florida State, where we have soon a study investigating microlunar Martian gravity adaptations of a number of different biological systems. A very comprehensive study, also one of the first studies exploring differences in physiological adaptations with women and men. With the next year Artemis II rocket, we have the first woman and person of color traveling to the moon. So these studies are very much tied to understanding what happens now that we have a broad diversity of individuals now traveling in space as well. And so in summarizing my academic and research experiences, my observation of the progress as an undergraduate trainee and now as a research faculty in terms of research was and tied to also technology available to us to conduct research. One example I wish to share is not my field, but a relevant topic is in the field of metagenomics, for example, where just a history of the field of metagenomics, which is the study of microbes in different environments, and the genetic adaptations of these microbes. And this as an example of how technology has led to the increase of our knowledge, and then also publication of findings as well, with some of the early metagenomic microbial research, so starting in the 1600s on the left, and then the arrow moving from left to right to modern day. Some of the early findings by Dr. Leeuwenhoek, reporting observations of microbiota in principle, and then some additional studies culturing microbes and understanding and learning their components, and very much tied to also the technology that was available throughout as history progressed, in terms of DNA sequencing, PCR, and then different variations of PCR, and then because of the incredible breadth of knowledge we're acquiring, subdisciplines being developed, focusing on specific subject matter within microbiology. And then this continued with more sequencers being available, and larger projects continuing to develop, and leading to projects in more areas across the world, in turn, understanding microbes in different geographic locations, and in turn increasing our global understanding of microbiology. And this figure here illustrates this increase in our knowledge in terms of publications from 1998 to 2015, in relation to sequencing technology available. And the green line here denotes the increase in release as the technology further developed as well. So what about in the context of citizen science? I learned that citizen science is also, in principle, has been an area that's existed for some time. So in the specific definition of the term has evolved and has become more specific. But even throughout history, there have been individuals that have been involved with science experiments that were not classically trained scientists, but were fascinated by subject matter and had contributions in various ways. For example, Henry David Thoreau had some observations of plant and animal life cycles in Concord, Massachusetts, and had details of this written down. And then the U.S. National Weather Service in 1870, as they began to make a forecast, they invited amateur meteorologists that had used instruments such as rain gauges and made some observations to include with the data that the U.S. National Weather Service was collecting. And then a few additional examples include in 1986, the Southern African Bird Atlas Project in South Africa relied on the observations of thousands of citizens to observe and catalog the environment and the different birds in that environment, which the project published later in 1992 and was much larger than and continues to be a citizen science initiative to date. The term citizen science specifically was phrased in 1996 by a lab in Cornell, and then continuing citizen science type initiatives to date include a few additional examples. Going back to Henry David Thoreau's historical records, scientists at Boston University collected those and invited additional citizens in the area to submit their own observations of the similar subject matter that Henry David Thoreau was collecting to expand upon that citizen science type initiative. And then now with with the explosion of technology and computers and the internet, those similar to my metagenomics example, those citizen type projects have also increased and scaled. With another example being in 2013, hundreds of citizen scientists, since 2013, hundreds of citizen science projects are ongoing across the world with millions of people participating in different capacities. So I'll provide some more specific examples of that in a moment. But one example I'd like to share just from my younger days is I recall one science project that I learned about was SETI, Search for Extraterrestrial Intelligence, which was a project that anyone with a computer could install a screensaver and have that screensaver running whenever the computer was idle. And when that screensaver was running, it would collect data from SETI's server, which were collecting through radio telescopes information from the universe and observing if there were potential signals from other planets, other solar systems that were indicative of life. And SETI developed a platform. It's been around since the 1990s, earlier, likely. But individuals could install a screensaver, collect information from SETI servers, and then the citizen scientists' computers would, in the background, analyze and analyze the data, and then share that back with SETI servers to make additional progress with regards to the research activities where that SETI was ongoing. And in turn, highlighting the option that technology provides us in terms of projects. We are from rotary telephones and analog cameras and notebooks and pens to now computers and iPads and cell phones and digital cameras that have incredible processing power. And in turn, an example is, in terms of processing power, this is a picture of NASA's mission control from the Apollo program. And still a rotary phone still present, and computers that have less processing power than any individual's phone like that each of you all are carrying. But with this project, in the context of Artemis II, sending individuals next year to the moon and back, with the Apollo program, with technology back in the 1960s and 1970s, less processing power than processing power in our phones, our modern phones, sent individuals to the moon and back. On that note, with regards to processing power and computational techniques, now we also have new technological platforms like machine learning and artificial intelligence platforms, which provide another set of tools through software and computers to organize and aggregate and learn large data sets. And just an overview of machine learning, with the concept of machine learning in terms of theory behind it, in terms of logic and syntax. Again, 1700s, 1800s, with Ada Lovelace laying the foundation for the first algorithm. Then Alan Turing developing a machine that could, the prototype of a computer. To fast forward to 2000s with neural networks being developed that simulate the behavior of neurons, and later Google developing larger scale unsupervised neural network that could be data being inputted to the systems and then interpreting and aggregating these data sets based off unique patterns that were embedded within the data sets. To now, another example being AlphaFold 1, in biomedical context, a technology that has the ability to predict protein structures. To supplement and complement, as just a few examples, research tools and technologies that are available to us. And the SETI example aside, one of my first citizen science project was with NASA's Hubble Space Telescope, which was a telescope launched in the late 1980s, early 1990s, which was an incredible advancement to understanding of astrophysics, capturing images from the billions of light years away from us here, and seeing the formation of galaxies, galaxy precursors, seeing the formation of stars, and aggregating thousands of images that were eventually placed into a platform where citizens could access these images and support NASA's initiatives and projects with the Hubble Space Telescope. For example, in the context of identifying images in terms of category, in terms of if they're stars, if they're galaxies, if they were doing some data quantification. So another example of a citizen science type project that had a grew my understanding of citizen science and led to my collaboration with a group of NASA investigators with our own citizen science project called Space Open Life Science Team for International Collaborative Exploration, with the focus being space biology, investigating the research that has been done studying how biology adapts in space environment ever since the 1950s, 1960s, with the early first days of sending individuals and an organism into space, to now the International Space Station, and just last year sending microbes and yeast to the beyond the far side of the moon, actually, and studying how biology in turn adapts to the spaceflight environment. And to preface the methodology and approach of our open science project, I'll provide a little bit of context of our research subject matter, where, as I shared before, the space environment is an environment where there's lack of gravity, there's radiation exposure, and here on Earth we're exposed to gravity, and gravity has a direct influence in terms of how our biology is oriented and behaves. One example of an organ system that adapts to a spaceflight is our cardiovascular system. Our cardiovascular system that transports our blood and and oxygen across our body, and in turn is designed to operate at certain conditions at the head, at our chest, at our feet, in line with the gravitational vector. Now, when we travel in space, the gravitational vector, it's a microgravity, so it doesn't disappear, but it's much, much, much less. So in turn, the position of our biological components gets reoriented. And in turn, there are a number of adaptations that result from that. Another example I shared earlier is that astronauts, they're floating in space, so they're no longer able to walk. And in turn, they have bone loss, they have muscle loss. And in turn, their cardiovascular system adapts. So from a research question, we are interested in what are those observations and how do these adaptations happen. And I highlighted the cardiovascular system, so just to orient everyone that may not have experience with this subject matter, the cardiovascular system includes the heart, arteries, capillaries, different parts, different components, lymphatics. And there's been a number of research studies in different capacities done of these different parts. But how much, what is our current knowledge of all these different parts of the cardiovascular system? Is one example, because I mentioned bone and muscle loss. There's also vision changes that happen with astronauts. So there are a number of different subject matter that is research in the field of space biology. So I'm just focusing on cardiovascular system for now. As I shared before, we have individuals on board the International Space Station traveling around planet Earth every 90 minutes. And they experience microgravity in certain conditions. Now, with the Artemis program, sending individuals to the moon and the intent to stay on the moon, that environment is different. Though it's in space, it's different. So in turn, I shared we have some ongoing studies in relation with those future missions to the moon. But in preparing for projects on the moon and around the moon, understanding our research to date to address potential unknowns or unknown unknowns that may occur when we travel to the moon would be incredibly beneficial to understand and prepare for. So that was a little bit about that's a little bit of the motivation behind our citizen science project, Project Solstice, which brought together subject matter experts across the space biology field focusing on, and I described parts of the cardiovascular system where we as a community organized relevant terminology, build a library of terms relevant to the specific cardiovascular research questions that we were interested in organizing and learning the research progress to date. With our focus being cardiovascular system, but also adaptations with humans, with rodents, primates. But there could also be studies of microbes, of plants, of yeast. There's been very small organisms that have flown into the spaceflight environment that research has also been completed. And we're also focusing towards microgravity. There are additional factors in the space environment that could be also researched as well with this citizen science approach. The effects of isolation, the effects of radiation, the effects of circadian rhythm changes, depending on the aim of the study. We co-led a team effort of subject matter experts, but developed a strategy to form this into a citizen science type project, where we were enthusiastic about inviting students, young professionals to contribute in diverse ways with this project. And in turn, there are various, in the space community, there are various student organizations that students get involved with to learn about NASA, learn about space projects, learn about what it's like to be a scientist, what it's like to be an engineer, what it's like to be, what kind of research studies are ongoing. One example being an organization called Students for the Exploration and Development of Space. So we had reached out to this organization and a few others, and highlighting with students and young professionals, we have a space biology study that we would love to have individuals with no previous scientific training to be involved with. And we received incredible enthusiasm. We had response from students that was unaware that NASA even did projects that were not rocket related, that they were science projects, and had students from all from different ranges of educational background, from community college associate level to postdocs. We had a number of undergraduate students, graduate, master's, doctoral training, as well as we had a global interaction with our project. We had students from across North America. We had students from young professionals from Europe, from Asia, from Africa, from South America, from Oceania, that were involved with our study in various capacities. That's part of our citizen science initiative. So how so specifically? Well, first, with a number of these students, this was the first NASA type project, first space biology type project, different from biology. My colleagues and I developed an educational platform to teach and show and educate these students about different subject matter relevant to this project, which included an introduction to space science, the history of space science, including an introduction in a little bit more detail than of the cardiovascular system, like I shared with you all moments ago. Then in turn, an outline and learning how the project was structured in terms of organizing the history of space biology, specific to the subject matter that we were focusing on, different ways to be involved with the project, in the context of knowledge synthesis, generating research questions, literature search. I'm going into more specifics of project structure, but educating the students how they would be involved with this project. What the specifics were, I highlighted the project was focusing on cardiovascular system and outcomes with rodents and people when traveling in space. And this first phase of our project, a pilot project, aimed to be a literature review, screening meta-analysis of these topics from the space biology field, where we were interested to organize knowledge, the research done to date, as well as understand the data changes in the specific cardiovascular parameters I shared with you on the table a few moments ago. And then, in turn, understand how these outcomes may be tied with additional adaptations that may be occurring with biology or people in traveling in space. So our study's design in principle was a literature search review and screening for the relevant literature. And then follow-up phase being a data extraction and additional analyses investigating across studies what was ongoing or what new hypotheses in terms of what adaptations were happening with these different studies. The platform that we had the opportunity to apply with our project was a platform called Competence, a screening meta-analysis platform that our FSU librarians and McGill University librarians and various librarians collaborate and support us in organizing the relevant literature and importing these into Competence. So this is just an image of one part of the platform before going to the screening component, with the screening component including seeing the collection of thousands of articles from decades of research organized specifically based off the search terms that we researched and we're interested in focusing on with our screening and meta-analysis study. And this is what our citizen scientists, our passionate students, young professionals would see and would in turn review in pairs, in teams, and review the literature, review the studies, and then identify the ones that were relevant to our project's area of focus. So for example, here I have, what they would see would be initially titles, abstract, based off search terms screen for our specific areas of interest. And we screen the students and young professionals screened for thousands of articles, where it was absolutely incredible the efficiency that we were able to identify specific studies, approximately 3,500 at the end of our screening project, of the close to 20,000 initially that were specific for the cardiovascular space biology studies that we were interested in. We also identified that doing comparison between, in terms of proficiency of citizen scientist screening, in terms of our instruction, that the number of articles, the y-axis here is number of articles, with the x-axis for citizen scientists that did not receive instruction, but then citizen scientists that received approximately 2 weeks of instruction, that the number of articles that they screened increased several times. and in short, showed the benefits of learning and being educated with regards to how to learn these screening, meta-analysis, citizen science approaches. And so in summary, that we completed our screening project with this approach, which with a more traditional approach would have taken about 2 years approximately to complete, based off previous experience. With our pilot project completed within 6 months. And a lot of lessons were learned. A lot of we are refining our citizen science project based off of the experience and feedback from our students and young professionals, as well as recently having the opportunity to share our preliminary project experience at a citizen science conference called Seaside, which is a collection of citizen science projects, over 2,000 projects with over 1 million volunteers and a number of members, and received some really wonderful feedback and in terms of how we could further evolve our this one example of our citizen science project, as well as resources available from the citizen science community to add more layers to our one example citizen science project. We also had, so this is also in collaboration with NASA's Open Science for Life in Space program. NASA has various similar type projects. One example being NASA Gene Lab, which is a collection of, is a database where users can, so space biologists have uploaded data from their different experiments, and citizen scientists can explore, investigate these data for additional studies, additional projects, additional analyses. There's an ongoing initiative to collaborate with various space biology researchers and develop more, in the context of data management, more cohesion in terms of ontology and approach across experiments. That our Solstice project, being a citizen science type initiative, is also involved with in terms of having citizen scientists involved with these different type of projects, and that's highlighted by Solstice being a project that NASA's Open Science for Life in Space has been very supportive of broadening and diversifying the projects that our pilot project has shown success with. So that was a summary of our ongoing citizen science project, and I wish to connect back with Students for the Exploration and Development of Space, a student organization. We have a chapter here at Florida State University. They had their first meeting back in 2022, but have had a number of events since then. Pictured here in the middle are some students at a local planetarium where they had a stargazing night, and a collection of students from all sorts of different backgrounds and disciplines, from biology, from engineering, from business, from education. Really a diverse cohort of students, having a number of events, like going to a local planetarium. They hosted a 3D printing workshop at the Innovation Hub, where students got to see and design and print based off of their design, little figurines, as well as ongoing projects like building a rocket, designing, building, and flying a rocket, as well as developing computational programming models, as well as having various monthly events, reviewing the history of our human space exploration efforts, like Women's History Month and Black History Month, in terms of, and many more. The various individuals have been involved with our space exploration project, and have had active conversation, learning from our Solstice program, reviewing and exploring citizen science project like the Hubble Space Telescope project I shared with you before, but now we have James Webb Space Telescope, which is, and then Kepler and various more, as well as additional projects and that the citizen science community has in a number of different subject areas, from ecology to political science, and that students have found a really wonderful, enriching learning experience to add to their courses, add to their research experience, and to connect with their ongoing experience and programs that they're involved with. So SEDS just being one example. So in short, I thank you all for your time and attention, and I really appreciate the opportunity to share a little bit about the projects that we have ongoing, and my experience from NASA, and my experience with NASA, and how it provided a wonderful set of opportunities for me as a first-gen academic to learn what it was like to be what it's like to be a scientist, an engineer, and contribute in different ways, and also now support many more students and young professionals in the context of our research, as well as through citizen science, open science initiatives. So with that, I'm happy to take any questions. Thank you.
Thank you for that. I'm really interested in the citizen science projects that you talked about, like Solstice. Mm-hmm. It's nice that, well, the space angle kind of helps to inspire people and capture their imagination and make them want to participate in these projects, right? But I'm wondering if there's an inherent problem with the massive number of sources of data you're dealing with, needing to organize and curate that data to make it useful. Is that a challenge for the project? Yes, that is a challenge and a significant consideration that we make, and the Covenants platform provides us one mechanism to approach that. In terms of, if I were individually to review and analyze the 20,000 articles myself, then that is a much more significant challenge than through a platform like Covenants, which allows us to, as a team, review that and break that challenge further. But that's where the importance of collaboration and the structure of our project team, having subject matter experts, having graduate trainees that are actively involved in doing the research, and then also having citizen scientists that are involved with in different capacities. And so we also define our project where we have various team meetings, we have evaluations, we have phases where we assess, reassess, and evaluate, and error check. And then also Covenants has also, I failed to mention this, but also has AI ML capabilities within in terms of aggregating and organizing. For example, based on search terms, seeing Covenants will do this naturally, move those relevant articles first, so those are seen first. But the complete LaSalle library is still researched. And we're also still in a pilot phase, so we're also still learning as well. But that's very much a significant factor that we consider. Thank you for the question.
Hey, fabulous.
Thank you, Dr. Riley.
Exciting stuff. So this morning when I'm driving in, NPR had a story about the James Webb Telescope and new results by looking at certain chemical composition of Europa. Mm-hmm. Europa, if you remember, is the moon that at the end of 2001, A Space Odyssey, humans are not allowed there. And anyway, so this is exciting stuff. And then, of course, last week was the capsule landing, which had grabbed, part of an asteroid and brought it back to Earth. So it's just exciting time to be here and explore all of this. And if you haven't seen the movie Contact, which is based on a book by Carl Sagan, you need to watch the movie or read the book. And the book is better, but the movie's not bad, except that they changed the ending that I didn't like. But anyway, it's still fantastic up until that point. So, hey, I hope you're going to keep us informed of all of these activities.
We'd love to. Really appreciate that, Dean Riley.
So I think that's all the time we have for questions. And thank you very much again, Dr. Narayanan.
Thank you for having me.